So if you have rho square, and if you have rho square, rho for pure state is given by this, and you have only one quantum state that is pure, that is entirely correlated to each other. And then you have rho square, Uiuc. And by definition of a quantum state, this equals 1. Okay, so this must be equal to that, and this is just equal to rho hat. Okay? So, but if you have a mixed state, then the quantum state is defined by this. I like to mention that psi j need not be orthogonal. Okay, psi j need not be orthogonal. Okay, need not be orthogonal. So some of the things that you have defined may not be correct. You might not be able to claim this. Okay, so for a mixed state, you can have a sum of quantum states. Those quantum states may not be orthogonal to each other. So it's not necessarily true that psi I, psi j is not equal to delta ij. Okay, this is not necessarily true for a collection of quantum states. And how do we prove what rho square should be? Rho square is then pi, pj, multiply both of them together. Okay, you have psi I, psi j. Psi j. Okay, you have this as the square of the density operator. And if you were to trace this thing, you would have this been equal to ij. Okay. To trace it, first you have to project into an orthonormal basis set. So the best thing is to just do this first, and then sum over n. That's how you trace an operator. If you do that, then you project the above into an orthonormal state. Okay, you would have that as the trace, and you have the sum over n, of course, sum over n somewhere. Okay. And then I can move this over. I can move this piece over here. And move that piece over there. And then combine the sign n and the sign n to make into an identity operator. Okay? And then rewrite this. Pi, pj, psi I, psi j, psi j, psi I. If we combine this and then collapse the identity operator, I get this, right? I make use of the fact that psi n, or phi n, n is equal to the identity operator. If I move that piece over there. So I get this. But these two, how are they related to each other? Yeah? The complex conjugate of each other. So that is just the magnitude square of that term. Okay? So this is just equal to psi I, very good, psi I, psi j magnitude square. Okay, but I say that these are not necessarily orthogonal to each other. These represent different quantum states. The quantum state that you're trying to describe is a mixture of these different quantum states. Okay? But they are normalized. Okay? So you know that if a vector is normalized but not orthogonal to each other, there is an inequality that this inner product satisfies. What is that inequality? Something like Schwarz inequality. It's like cosine inequality that you have if two vectors are not orthogonal to each other. They are always having a cosine angle between them, right? So this is always less than or greater, less than or equal to 1. This is like the cosine inequality. Or maybe like the Schwarz inequality. It goes by different names depending on where you encounter this inequality. So because of that, then this must be less than or equal to pi pj I comma j. Okay, but this is just equal to sum of pi sum of pj multiplied with each other out. And what does this sum equal to? 1, right? This sum is equal to 1, so this is just equal to 1. So this must be equal to 1. So trace of rho hat square for a mixed quantum system always has this property. So this should be equal to actually an equality here. Okay? But trace of a pure quantum system is quite clear that the quantum system density operator square is the original density operator. If the quantum system is pure, then the trace of that rho hat is always equal to 1. So for mixed quantum system is always less than or equal to 1. So that is the distinguishing feature between the mixed state and the pure state. Okay, are there any questions regarding this proof? Then we can use the density operator method or the density matrix method to describe the state of the quantum system. For instance, we can use that to describe the state of a laser system. The laser system might consist of many atoms. So maybe not a truly laser system. A truly laser system is quite complicated. You need a 3-level system. But let's assume that you have a collection of atoms. Each of these atoms have an excited and a ground state, or lower energy state and an upper energy state. And then we like to excite this with a light. When the light comes in, and excite this ensemble of atoms. Some of the atoms will be excited to the excited state because they absorb a photon from out there. And some of them will not be, okay? But if you excite all of them, each of them can be described by a pure quantum state, for instance, okay? But collection of these atoms, you can describe them as a collection of mixed states. And some of them have already collapsed to the ground state, some of them are in the excited states, okay? So a density matrix is very useful for describing this kind of quantum system. Okay, so we would like to derive the general equation of motion for a quantum system using density operators. So we like to use density operator or density matrix to describe what the state is in, and we like to figure out what the time evolution of this. If this density operator changes with time, how does it change with time? Okay, let's derive some of the formulas for this then. So let's assume that we have a density operator that is described by just the outer product between two state vectors. Then if you were to find the time evolution of this density operator, it would be equal to, if I use this subscripted notation, the time evolution of the first vector times this plus this times that. Okay, and let's assume that the wave vector satisfies some sort of the Schrodinger equation described by a Hamiltonian. And we can use Schrodinger equation to simplify this Hamiltonian, the time derivative. Okay, we know that this is true. I over h bar, the Hamiltonian of the system times psi. This is the general way to describe the Schrodinger equation. Okay. Do I need the minus there, right? I need the minus. Otherwise, okay, I omega it doesn't come up right. Okay? I need a minus sign there. Okay, so this is general form of the Schrodinger equation. So if I plug that in, then I would have the time evolution of the density operator, which describes the state of the quantum system, can be written as minus I over h bar h hat psi for the first term, okay, plus this is the complex conjugation transpose. So you can write that this is the transpose of that equation you can use the second equation and plug that into this second term. You will get something like plus I over h bar psi h hat. Okay, you will have that as your equation, and then if you pull out a rho hat, and this is just your rho hat, this is just your rho hat, right? So this is the same as I over h bar rho hat, h hat minus h hat, rho hat. And this is called the commutation I over h bar rho hat h hat. So the time evolution of the density operator is just given by its commutation with the Hamiltonian operator of the system. So if you know the Hamiltonian of a system, you can find out how the density operator will evolve with time. But density operator is just a description of the state of the quantum system. You will know how the state of the quantum system is evolving with time. Okay? So you can prove this. Even if rho hat is a mixed state, this still holds true. If you have this kind of quantum system, you can go through the proof again. You can plug that in and prove quite easily that this still holds true. Okay. This is good for both pure and mixed state. Okay. This equation is good for both. And you can take the matrix representation of this operator equation and show that it also is true for if I was to have rho nm is equal to phi n rho hat phi m, I can also show that this equation is true even for that kind of matrix operators. It's quite easy to show. You just take the matrix representation of this equation. You take this equation and you multiply it from the right hand side by maybe psi sub n, and then from the left hand side by psi sub n. Just take the inner product of truth. Okay, and assuming that psi sub n and psi sub m are independent of time, they're not functions of time. Okay, they're constants of time, then on the left hand side you will get something like dt rho nm. And then you will have IH bar psi n rho hat h hat phi m kind of thing, minus psi sub n h hat rho hat psi sub m kind of thing in the middle. Okay? And then you can insert another identity operator in there. Psi, let's call it P. You can insert in there and convert this into a matrix operator. You can do the same thing over here. So finally, you just can show that the time evolution of the density matrix operator is the same as I over h bar, the commutation between the density operator in the matrix form with the Hamiltonian operator in the matrix form. This is also true. So if you know how to find matrix representation of an operator, you get those to be correct. Those are the equations of motion for the density operator, which describes the state of a quantum system. So let's use that to describe the interaction between light and an ensemble of atoms. Okay, light and an ensemble of atoms. And let's assume that each atom has a two-level system to simplify things. Two-level system. Okay, there are many two-level systems, or many systems in this world that can be approximated by a simple two-level system. Many of them. And in order to make the mathematics simpler, many people also study just two-level systems. Okay? So there are many of them. One is the NMR system. NMR, MRI is spin up, spin down system. Right? The spin is either up or down, then you will have different interaction energy with the magnetic field. Two-level atom. Excited. And ground state. I guess you can also have a superconducting system. Okay. Like if you was to study, say, Josephson junction. You can describe a superconductor into two regions. You will have a Cooper pair in this region and a Cooper pair in that region, and you can study the coupling between these two Cooper pairs. Okay, and then you can describe that as a simple two-particle system. Okay, a superconductor, just the junction, and there are many others that you can think of. And let's just use the density operator method to study such a system. And usually, such a system will involve coupling between two states. And that the coupling between two states can be simplified greatly as being state 1, and then having state 2. Okay, let's assume that before coupling occurs, the two-level system is described by these two equations. These two equations are greatly simplified form of Schrodinger equation. We assume that this is some sort of h hat psi 1, and this is some kind of h hat psi 2. Psi 1 and psi 2 are eigenfunctions of h hat, and they simplify to that form. And in a simple two-level system where no coupling occurs, this is how it looks like. But now assume that there is some coupling, like this two-level atom system. Then you have to modify this system with some kind of a coupling between the two. Okay, you do some modification, assume that some coupling occurs, and that some energy from some wave function from eigenstate 1 can affect the wave function in eigenstate 2, and the wave function from eigenstate 2 can affect the wave function in eigenstate 1, and you describe this by this kind of very simple coupling system, usually called a couple mode equation. And these kind of equations have been used a lot even in waveguide theory, in electromagnetics, in all kinds of systems when you just are interested in the physics of the coupling, not interested in the detailed mathematics. So you describe the system in such a simple manner. Okay. So we can use that to describe this ensemble of atoms and see how we can derive some simplified equation. This ensemble of atoms in general would be described by something that looks like that. And in general, an atom will have many eigenstates, okay? It will have many eigenstates. There will be many of those. As you can see in the quantum world that you study simple quantum world, 1D problem. You find that you have the ground state, you have the first excited state, the second excited state, and so on. And this is 1D. If you convert into 3D, you have a world that looks something like this, and then you will have the hydrogen atoms, and then you have different kinds of sp_d, f orbitals, very complicated things in 3 dimensions. Those are just trapped states. And usually the number of eigenstates you have in an atom is huge in number. But let's simplify things. Let's assume that the quantum system that describes the atom can be simplified to just having two levels that are of interest and of importance to us. So how do we simplify such a complicated system into a simpler system? We use the subspace projection method. We say that psi can be written as ai psi, a1 psi 1 plus a2 psi 2. If we use a finite basis method or subspace projection method, we say we are only interested in that two states. And we are going to do experiments close to that two states. Okay, you might have many energy levels. Okay, maybe I'm only interested in this two energy level. And I will shine my light with frequencies that only interact strongly with that two levels. As you can see in the Fermi's golden rule, okay, you can actually selectively excite certain atoms for the excited states, right? So if that is the case, I say, if I'm only doing experiments in this vicinity, I can approximate the quantum state as a linear superposition of these two states. Then, if you plug that in as you have done in the finite basis method, you will have something like psi1 A1 on the right hand side plus A2 psi2, and then you will have something like IH bar dt, maybe A1 dt psi1, or A1 can be a function of time actually, so I shouldn't put it outside the thing. Psi. And then you try to find the matrix representation of the Hamiltonian under this subspace. You try to find the matrix representation of the Hamiltonian under this subspace. And then, if you do things correctly, and if this Hamiltonian corresponds to the case when there's no external light, it's just an atom sitting there by itself, what you have would be just two diagonal systems, E1, 0, 0, E2. H hat would be just approximated by this. I don't know if you can see that if you were to find a matrix representation of this Hamiltonian operator using the subspace projection method, okay? And you will find that this is the system that you work with. I can maybe elaborate that a little bit more. Let's say we are interested in the eigenvalue problem. A1 psi 1 plus A2 psi 2 is equal to E A1 psi 1. Let's convert the right hand side into an eigenvalue problem. So if you now multiply this equation by psi 1, then you get A1 is equal to A1 EA1, right? EA1. If you multiply by psi 2, you get A2 is equal to E A2 kind of thing. So you have completely a diagonal system, which is E1. I should actually, on the left hand side, I should have already E1 here. On the left hand side, I should have E1 here, I should E2 here. Okay, so I would have A1, E1, A2, E2 here. On the left hand side, if I were to take this to be the eigenfunctions of this to be the eigenfunctions of that, then I have E1 and E2 on the left hand side. And if I convert this into an eigenvalue problem, I would just say that this is equal to E psi, right? And then psi can be expanded such I get on the right hand side. And then on the left hand side, I will have this very simple system. A1, A2. I just have this very simple system. It's quite clear what the eigenvalues are. In this subspace projection method, E is to the E1, E2 are the eigenvalues of the system. So I have projected a very complicated quantum system into a much simpler one, described by two states of the quantum system using this subspace projection method. But now I say that this is not the complete Hamiltonian that describes a system as you have learned in perturbation theory, that if there's an external light, you have to add in a perturbation Hamiltonian. So the Hamiltonian is actually the non-perturbed Hamiltonian plus a perturbation. Okay, if you put in external light, that perturbation, you can think of it as an electric field, okay, that is proportional to Z, Z being the position of the atom. You can take the origin of the atom as the coordinate origin. So ZE is equal to P kind of thing. So you can see that this kind of potential gives rise to an E field. The E field that is polarized. And if able to take the gradient of this potential, we get an electric field pointing in the z-hat direction. So if you have an electric field present in the vicinity of an atom, you can think of the potential as being modified to include this extra term. Okay, this extra term is a perturbing potential. It's a linear potential which corresponds to an electric field. So if that is the case, then we will have to change the Hamiltonian by a little bit. And we can think of the perturbation potential, Hamiltonian, the electric field. This is the electric field amplitude times the dipole moment, where mu hat is something like an EZ hat kind of thing. Okay. This is not a unit vector, but this is a position operator. This hat here means that this is a position operator. And then if I were to find the matrix element of this under the subspace projection method, I will need to find this under the two bases that I have found, psi 1, psi 2, or psi I, psi j. In the perturbation method, I will use this to find the perturbation Hamiltonian. And I can pick psi 1, psi 2 from here and try to approximate and estimate what this Hamiltonian would be under the subspace projection method. And if I work this out, okay, I will get that mu ij, okay, mu ij, and that would be equal to minus E psi I z hat psi j. This z hat is not a unit vector, it's a position operator. And in the coordinate space representation, this z hat becomes z. Okay, this position operator just becomes z. And it might be some other things if you're in other spaces. The z hat would be different. But in coordinate space, it's just z. Then you can say that if a wave function, in general, if I equals j, psi I is not equal to 0 because this is normalized. Okay? And this is normalized, and this is not usually equal to 0 because this is an even function of space. Okay? Now if you were to put a z function in between, okay, this makes it into an odd function of space. So this would always become 0 if you put this in between. Okay? Because you can say that this might have odd parity, which means that it's an odd function of space. This has an odd function of space. But when you multiply them together, you make them into even function of space. They evaluate not to 0. But if you introduce an odd function, it always becomes 0. So it happens that psi 1 z psi 1 is always equal to 0. Psi 2 z psi 2 is always equal to 0. But then the cross term is not equal to 0. Okay, because one of these will have odd or even parity. Okay, when you multiply it by z, you make that into even function. And usually it happens to be this way, not equal to 0. So if you look at this matrix element, the diagonal terms are always equal to 0. The off-diagonal terms will be non-zero. So if you look at this perturbing Hamiltonian projected into this subspace, it will only contribute to the off-diagonal elements. Okay, it will not contribute to the on-diagonal element due to this parity consideration we have over here. So if you look at this Hamiltonian now, under the subspace projection method, in that very small subspace that we have used to describe the quantum system, it just becomes something like that. Okay, the perturbing Hamiltonian would just look something like that. Okay, where mu d is just mu12, where mu12 comes from here. Okay, mu d is just mu12, which is equal to mu21. Okay. So now the total Hamiltonian to describe the system is just that one. I should actually call this E2. I'm sorry, this is a two-level atom, so you have two different energy levels. So I should call that E2. So the total Hamiltonian, which is just the unperturbed Hamiltonian plus the perturbing Hamiltonian, is given by E1 minus E mu d E mu d E2. Okay? So that is the simplified, greatly simplified Hamiltonian to describe the interaction of these atoms with light. Okay? Greatly simplified Hamiltonian. Because we only focus on two levels, E1, E2. Okay, E1, E2. And then just look at the problem in the vicinity of this region. So, we have derived the equation of motion for the density operator with respect to the knowledge of the Hamiltonian. We also derived the equation of motion for the matrix representation of the density operator. If you know the matrix representation of the Hamiltonian. So we can use this equation to describe the equation of motion of the density operator. This is actually just H bar. Okay, this actually has been projected into this subspace, and this